Hello and welcome to all students. In this lecture, we learn about polynomials over R. Let x be an unknown quantity to be determined which commutes with real numbers for a positive integer n. Let x raised to the power n is equal to x into dot x n times, and x raised to the power 0 is equal to 1. 1 into x is equal to x. Okay, so then the polynomial over R is a finite expression of the type f of x is equal to a naught plus a1x plus a2x square plus dot plus an x raised to the power n, where each I from 0 to n is a real number and is a integer, positive integer, and a naught is not equal to 0. We note here the arbitrary constant x is called the indeterminate, ai's indeterminate, and the coefficients ai's are called the coefficients. N is called as degree of n is called as a degree of that polynomial, and an the highest degree term of the polynomial is called the leading coefficient. An is a coefficient of highest degree, coefficient of highest power of x, and an is called as leading coefficient. So whenever the leading coefficient an is 1, then that polynomial is called a monic polynomial. So for example, monic polynomial is suppose x square plus 2x plus 3 equal to 0, and here x square is the highest power term having highest power, and the coefficient of x square is 1, and that's why this polynomial is called as a monic polynomial. A naught is called the constant term. It is the coefficient of x raised to 0. If any term x raised to I greater or equal 0 less than n does not appear in the expression, it means that the coefficient of x raised to I is 0. The zero polynomial is called one whose all coefficients are 0. For example, 0 into x square plus 0 into x plus 0 equal to 0. So here in this polynomial all coefficients are 0. That's why this polynomial is called as zero polynomial. Okay, the zero polynomial is the one whose all coefficients are 0, and the degree of zero polynomial is not defined. A constant polynomial has only a constant. For example, f of x is equal to 5. Okay, this is a polynomial. It is called as a constant polynomial because it has only one term 5 and it is constant. The degree of a non-zero constant polynomial is 0. The set of all polynomials over R is denoted by R of x. So R of x is the set of all polynomials with the real coefficients. Algebraic structure of R of x. Algebraic structure of R of x. So first algebraic structure we see, it is equality. Two polynomials f of x is equal to a naught plus a1x plus a2x square plus plus an x raised to the power n, and g of x is equal to b naught plus b1x plus b2x square plus plus bm x raised to the power m in R of x are said to be equal if and only if m is equal to n and ai is equal to bi for each I. Means two polynomials are said to be equal if the degree of these two polynomials is same and the coefficients of same power of x are also same. Okay, so let us we define the next algebraic structure. We call it is addition. Suppose we have two polynomials, f of x is equal to a naught plus a1x plus dot dot plus an x raised to the power n, and g of x is equal to b naught plus b1x plus dot 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 plus bmx raised to the power m are two polynomials in R of x. Then f of x plus g of x is given by f of x into g of x is given by a naught plus b naught plus a1 plus b1 into x plus dot dot an plus bn x raised to the power n if m is equal to n, and a naught plus b naught plus a1 plus b1 into x plus dot dot plus an plus bn into x raised to n plus b n plus 1 x raised to the power n plus 1 plus dot 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 plus bm x raised to the power m if n is less than m, and the third expression. So the addition of these two polynomials is defined like this. Okay, it follows from the definition of addition that, so first thing is the addition is a binary operation in R of x. Means if we have two polynomials in R of x, f of x and g of x belongs to R of x, then their addition f of x plus g of x is also belongs to R of x. Means if we have two polynomials in x with real coefficients, then their addition f of x plus g of x is also a polynomial in x with real coefficients. If f of x plus g of x is not equal to 0, then addition is not equal to 0, then degree of f of x plus g of x is less than or equal to maximum of degree of f of x, degree of g of x. For example, f of x is equal to 3 plus 2x plus 5x squared minus 6x cube, and g of x is equal to 4 plus x minus 5x squared plus 6x cube. So here two polynomials are given and their addition is 7 plus 3x, and its degree is less than degree of f of x and degree of g of x. So addition is associative and commutative in R of x. So we know that what is meant by associativity and commutativity. Okay. Because the addition is associative and commutative in R. The zero with respect to addition is the zero polynomial in R of x, and the negative of the polynomial f of x is equal to a naught plus a1x plus a2x square plus dot 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 plus an x raised to the power n is given by minus f of x is equal to, just give the negative sign to each coefficient of x raised to n, each coefficient of x in each term, just give the negative side to the coefficient. Now we define the multiplication of two polynomials. If f of x is equal to a0 plus a1x plus dot dot plus an x raised to the power n, and g of x is equal to b0 plus b1x plus dot 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 plus bn x raised to the power m are two polynomials in R of x, then f of x into g of x is equal to, so we have the multiplication of two polynomials like multiplication of two brackets, a plus b into c plus d, and the multiplication is ac plus ad plus bc plus bd. So like this we can multiply these two polynomials. So multiplication of two polynomials is again a polynomial. F of x into g of x is equal to summation I runs from 0 to n plus m ci x raised to the power I, where ci is given here. Okay. It follows from the definition of multiplication that multiplication is a binary operation in R of x, and it is also a binary operation. Binary operation means if we have two polynomials in R of x, then their multiplication is also belongs to R of x. So multiplication is associative and commutative in R of x. The identity with respect to the multiplication is the constant polynomial 1 in R of x. If f of x is not equal to 0, g of x is not equal to 0, then their product is also not equal to 0. F of x into g of x is also not equal to 0. Let f of x and g of x be two non-zero polynomials in R of x. Therefore, if f of x is equal to, we have two non-zero polynomials, therefore their coefficients are not equal to 0. Constant term is also not equal to 0 in both the polynomials. But in the case of an bm not equal to 0, by the cancellation law in R, f of x into g of x, what we have is this: the degree must be n plus m, cannot be 0 in R of x since it contains at least one non-zero coefficient, namely an into bm. Therefore f of x into g of x is not equal to 0. The cancellation law holds in R of x. If f of x is not equal to 0 and f of x into g of x is equal to f of x into h of x, and g of x is equal to, then g of x is equal to h of x. So cancellation law holds in multiplication of numbers. So similarly here cancellation law holds in multiplication of polynomials also. If f of x is not equal to 0, and if we have equality f of x into g of x equal to f of x into h of x, then f of x will get cancelled, and what we get is g of x into equal to h of x. Okay. If f of x into g of x is not equal to 0, then the degree of f of x into g of x is equal to degree of f of x plus degree of g of x. The inverse of any polynomial with degree greater than or equal to 1 does not exist in R of x. It can be proved as follows. The proof is given here. So let us stop here. Thank you.